Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as every night during Advent of Code, we're going to be working through the puzzle solutions in C++. Thank you to everyone who's watching the live stream on Twitch, and also everyone who's watching the stream replay later on YouTube. As always, if you're watching on Twitch, see the channel description. You can find links to my YouTube channel for the stream replays and the GitHub repo where we post all of the code that we write. If you're watching on YouTube, just check the video description right down there. You're going to find links to the live streams on the Twitch channel, and once again to that GitHub repo with all of the code. So I'm starting the stream just a few minutes early tonight because after last night's stream, I did some refactoring. You might remember that last night we wound up copy and pasting some code from a previous night's solution to deal with a two-dimensional grid of numbers. And I figured, well, if we use that twice, we should probably abstract it out into a library and maybe figure out, some additional things that would be useful to that. So I took a crack at writing this two-dimensional geometry library called Grid2. And this is already uploaded in the GitHub repository. You can check out the code there. But basically, this library in this AOC 2021 Grid 2 namespace has a few concepts in it. It has a point with X and Y coordinates, and that point we can see if it's equal or not equal to another point. We can hash it, so we can use it in hash-based containers. And it also has methods that gives us all the adjacent points in cardinal directions, and then all the adjacent points in cardinal directions and diagonal directions. Now, you'll notice there are a couple of operator overloads here with another class called vec. Well, or actually it's a struct, but this struct vec represents a vector in two-dimensional space. And so it can represent the difference between 2 points or just, a direction to move, something like that. So vector has, dx and dy. You can think of those as, the deltas in each of those dimensions. It also has equals and not equals operators, so we can see if one vector is equal to another operator. It has negation operator so that you can, take the negative, reverse all of its dimensions. You can add and subtract vectors from each other, and that's all the operators that we have here. Then there are a few other convenient methods. There's one for the Manhattan distance, just to figure out how far a vector goes according to the Manhattan metric. There's another one, magnitude, that uses the Pythagorean theorem to calculate its actual proper magnitude in Euclidean space, by just taking the sum of the squares of those deltas and then taking the square root of that. There are methods to tell whether the vector is horizontal, vertical, or a 45-degree diagonal. There's this unit step method, which, what it does will become more apparent when I actually show the unit step method. But basically, if the vector is horizontal, vertical, or a 45-degree diagonal, then this produces a vector that only has deltas of 1 or 0 in each dimension that you can, apply to take unit steps along the grid in the direction of that vector. And finally, this is also hashable, so it can be used in hash-based containers. We have this class of x, which has, useful constants for vectors, going left 1, right 1, up 1, down 1, one that's an array of all the cardinal directions, one that's an array of the diagonal directions, and this k-adjacent 8 is both the cardinal and the diagonal directions. Where stuff starts to get pretty cool and really take advantage of the features of the C++ language, particularly the ability to do operator loading, is these overloaded arithmetic operators that allow us to do arithmetic between points and vectors. So, for instance, we can add a vector to a point and get a new point. We can subtract a vector from a point, same deal. We can subtract one point from another to get a vector, to find the vector that represents the path between them. and we can add a vector to a point to get another point. Or we can, subtract a vector, same thing. And then finally, we have this one that is a little bit fancy, but basically it's a template where if you have a container, like a vector, like a C++ vector of geometry vectors, then it will add all of those to the point and give you a C++ vector, the container, of the results. Then finally, there's this grid class, which represents a dense two-dimensional grid in space, like we've been dealing with on several of these puzzles. And each cell in the grid can have a value attached, this type named t. So there are iterators to visit all the cells or to visit all of the points that are in range of the grid. There's a method to read it from the input of the format that we've been seeing so far. And there's ways to see its horizontal and vertical size. There's this method that checks if a point is within range of that horizontal and vertical size. There's this method which will take a container full of points and filter it down to just those that are in range. There's accessors where you can provide it with a point and it will give you a reference to the value at that point. Then there's all this iterator stuff where you can iterate over all of the points in range or all of the values that are held in the grid. And so with this, I've gone back and redone the solutions to, I want to say, was it day 5, day 9, and day 11? It's definitely day 9 and day 11. There was one more. But basically, we can reuse that common code that handles the geometry for us and wind up with a shorter and simpler solution. So for our octo map, we use that grid class to represent the energy levels of the octopi. And then for a step, we just go through all the points in the grid here. We put stuff in our pending flashers like usual. And then when we need to find, adjacent points, then we just say, on that flasher, we say adjacent with diagonal. That's going to give us all the points that are adjacent to a given point. We filter that to those that are just in range of the grid. And then we have our list of adjacent cells to work with. So we've kind of abstracted out all the handling of the geometry to that common library. I actually went a little buck wild and I started working on a similar thing. It doesn't actually have a grid class yet, but to do n dimensions. So, 3, 4, however many higher order of dimensions, we can kind of generalize points and vex to that. I'm not really going to talk about that too much yet unless we have to start to use it on tonight's puzzle, though. So who knows if we have to use that tonight? We'll find out in about 20 seconds what tonight's puzzle is. But I figured that it would be a good idea to, pull that out into a reusable library in case we need to use that same kind of logic again, because we've already seen it a couple of times. All right, day 12's puzzle, ready to go. Passage pathing. With your subterranean systems subsisting suboptimally, the only way you're getting out of this cave is by finding a path yourself. Not just a path. The only way to find the best path is to find all of them. Ugh. Fortunately, sensors are still mostly working, so you build a map of the remaining caves. So start A, start B, A to C, A to B, B to D, A and B. Okay. So this is a list of how the caves are connected. You start in the cave named Start, and your destination is the cave named End. An entry like B to D means that cave B is connected to cave D, so you can move between them. Okay, so this is an undirected graph, it looks like, and it's showing us all the edges. Goes to find a number of distinct paths that start, end at end, and don't visit small caves more than once. There are two types of caves. Big caves, written in uppercase like A, and small caves, written in lowercase like B. Be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting multiple times. So all paths you find should visit small caves at most once and can visit big caves any number of times. Given these rules, there are 10 paths through this example cave system. Okay. We've got ourselves a search algorithm to write. Okay. How many pass through this cave system that visit small caves at most once? Okay, so we've got to do a search through all of these and figure out how many total paths there are. Okay. Let's look at what that input looks like. Okay. Not a huge cave system, but we'll go ahead and we'll first include the check and IO libraries because I got a feeling we're gonna need them. So the first thing that we'll do is just put together a list of edges in this cave. So these are undirected edges. You can go back and forth on them. So we'll make it so that you can look up from either end of an edge. So I think that well, first things first, let's get our input as a as a vector of strings. Call that edge lines, and then we'll use our normal read lines from file routine to read the first argument to the program into those edge lines. And then I am going to use a flat hash map. It's absol/container / flat hash map. We're going to be using both the map and the set, and why that is will become apparent in just a second. So we're going to build up our list of So how this is going to work is for a given cave, we're going to have that cave's name, and then it's going to map to all of the other the set of all the other cave names that are connected to it. So we're going to go through each of these edge lines, and then we're going to split it by that dash character, and we should have the start and the end on either end of that. Not standard string literals, just standard string. We will use abcel stir split. Here, I'm just going to include the header for that so we can get our autocomplete going. So we'll use stir split on the edge line with that dash character to get the names of the caves. We should have 2 of them. And then what we will do is for either direction we'll add the opposite cave on that path to the set of reachable caves. So edges dot front dot insert caves.back, and then also do it in the reverse direction. So caves.back.insert caves.front. Okay, so now we know our map of reachable stuff, and we know we have to start at start and find our way to the end. and then count up the number of paths that it's okay to take. So we're going to use a recursive algorithm to approach this. And we'll just use, an anonymous namespace to put all our helpers in, like we usually do. But we're going to say, like, int count paths. And we're going to have the edge map as a constant parameter. We'll let the auto formatter handle that once we write out all the parameters. We need to know we'll also have a flat hash set of strings for the small caves that we've already visited, because we do not want to revisit any of those. And then we will have a string to represent the current cave. So, okay, formatting that more nicely. So if the current cave is the end cave, then, there's one way that we can reach it here, so we'll go ahead and return 1. Otherwise, we need to look at all the other caves that we can access via the edges and try to go to those that aren't already in our set of visited small caves. So we'll say or actually say if visited small dot contains current cave, then we're going to return 0 because we've already visited the current cave, so we can't hit it again. I'm not sure I want to make that responsibility, though. Let me think about that. I'll come back to that. But basically, so for the next caves that are in the set of edges accessible via the current cave, it doesn't like that subscript because it's const, so we'll just use at. Then if next is not in the set of visited small caves, then here we will go ahead and insert it, and we will say paths plus equals a recursive call to this count paths with the same edges, with this visited small set, and then next will be the current cave for that. And then when this returns, we need to be sure to erase that from the visited small set if we didn't already visit it. I realize now that I'm doing contains and insert separately, and that's going to incur 2 lookups into the map, and we could make that a little bit more efficient by doing 1, but it's slightly more clear this way, so I'm just going to leave that as is for now and maybe come back and optimize that later. So return paths. This might actually be all that we need for this. Oh, you know what? The other thing, no, we need to deal with the fact that a path can, that a big cave we can revisit. So, we'll say if abseil ASCII is upper, we'll just use the first character of next. Well, okay, if it's not uppercase, then it's small, and we'll put it in the list of visited small. And we will also only erase it if it is a small cave. So we'll put that in the visited small set. So that's the one thing we were missing. And I think now, and we can just put, we can start our, our set of visited small caves should initially be just the start. So now we can run our count paths. We've got our map of edges. We've got our visited small cave set. And our initial current cave is start. Okay, as far as dependencies, we're going to need flat hash map, flat hash set, and strings from abseil. So let's go to a previous day that has all that, that has at least some of that we can copy and paste into deps here. Oh, we're also going to need to put in the deps for the various utility libraries, but come on. Flat hash map, flat hash set, strings, and from our little utility library, we're going to need check, and we're going to need IO. Now, before I try and build this, oh, forgot a semicolon there. Okay. Now, let's try and run it. And run it on our day 12 input there. Okay, it says 4,011 paths. We'll see if that's correct. Seems like kind of a lot, but we'll see. All right, that's correct. And we're in the top 1,000. Let's go on to part 2. After reviewing the available paths, you realize you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times. A single small cave can be visited at most twice, and the remaining small caves can be visited at most once. However, start and end can only be visited exactly once each. Once you leave start, you may not return. Once you reach end, path ends immediately. Okay, so there are more paths by this rule. Okay. So we are allowed to visit only one small cave twice. Okay. Well, first things first, I will go ahead and make a commit with the first part of this solution. And I will go ahead and copy the source code for part 1 to part 2. And now we can begin to ponder it. So can visit a single small cave twice. So the like we can always keep track of on a given path if we've hit a small cave twice. I wonder though if there might be an issue with overcounting there because we could generate the same path two different ways. Not actually sure about that. Just as an experiment, see if this works. I'm going to add, you know, some Boolean here called, you know, double small. And we'll set that only at the second time that we've reached it. So we'll say, so let's see. Okay. So we'll say else if not double small, meaning that the next cave that we want to visit is in the set of small caves that we've already visited, but we've not doubled up yet. So and it's not start. If we get to end, we're still going to return 1 anyway, so it doesn't matter. I mean, we're not going to further expand out from end. But but we can't revisit start. So if not double small and next does not equal start, then what we can do here is essentially the same thing, except we're going to set double small to true in this case to prevent this from happening again. So maybe this is all that we need for part 2. I'm willing to give this a try, but it's entirely possible we've missed something. Oh yeah, we actually need to make the build target for part 2 in order to do that. All the dependencies are the same. Only the names have been changed to protect the innocent. Okay, 108,035. Let's see if it's correct. All right, 490. That's, I think, our personal best for this year. We're in the top 500. So yeah, this one was just kind of a basic pathfinding exercise, and you know, all you got to do is just keep track of where you've been. Yeah, it's easier to know where you're going when you know where you've been. That's why it's important to study your history, folks. My cousin, who is a professor of American history, would be very proud of me for saying that. But once again, I want to thank you all for watching tonight. I am very pleased with how quickly we got this tonight. I think this is one where it's a very simple kind of graph theory problem. But the important things to recognize about this problem were, one, that all the edges in the graph were bidirectional. So if we make a lookup graph for, what caves are accessible from a given cave, you got to make sure to have the links going in both directions, which is fine. And then you just keep maintaining that set of small caves that you visited to make sure you don't visit one twice. And the modification for part 2 is relatively easy. We just added in that Boolean condition to keep track of, hey, have we been to a small cave twice? And it all worked out okay. So, yeah. Thank you very much for watching, both to the folks on Twitch, on the live stream, and the folks watching the YouTube replays later. Again, if you're watching the live stream on Twitch, check the channel description. There you'll find links to the YouTube channel for replays and to the GitHub repo where all the code goes. If you are watching later on YouTube, just check the video description right down there. You're going to find links to the Twitch channel and once again to that GitHub repo. Thanks again, everyone, for watching. I hope you had fun with me solving these puzzles tonight, and I will see you again tomorrow night. Bye-bye.